welcome to Properties of Matter. Right, so this is a brand new unit. You should all have the course notes which you got before Christmas, and so you'll have your brand new booklet. It's going to be the same as we've always done. There's notes describing what I'm going to be talking about in the video lessons. Um, but let's just jump right in and look at the learning outcomes for this. Okay, we can see in the first bit, so properties of matter, specific heat capacity. I'm going to just skip through these first two ones, so I'll come back to that in a little bit. But I am able to explain that the temperature of a substance is a measure of the mean kinetic energy of its particles. So we'll do that first, and then we'll go back and look at, in the main specific heat capacity lesson, we'll look at these three items here. So what do I mean by heat and temperature? You may have assumed that they were meaning the same thing, but actually heat is very much an energy, and so we'll talk about heat, and when we talk about heat, we're actually referring to an energy. And I'll explain more about what heat energy is. And then we've got temperature. Now, temperature is how hot or cold something is. And so temperature is what you'd be familiar with, the temperature outside, the temperature of a cup of tea. It's measured in degrees centigrade, and you'd be well familiar with that. But what actually is heat energy? Well, heat energy is referring to the kinetic energy of the particles within a substance. Everything vibrates, and so you would have, if you think about your particle model of a substance, if I come to here, I'll just draw something out for you quickly. Okay, so if we have a solid, now if you remember, you've probably done this in first and second year, whether you remember it or not is different matter, but the particle model of a solid would look something like this. You would have tightly packed particles that are arranged in a kind of regular fashion. With a liquid, it would still be as tightly packed, just about, but they would be in a more random fashion. A solid being a solid, in the way that the particles are arranged, you can't really move it, which is hence why it's known as a solid, and it has all the properties of being a solid material, such as that it won't be able to bend or pore. With a liquid, the particle spacing is around about the same, but the actual bonding, don't want to talk about bonding here because there's no chemical bonds in between the individual particles, but the sort of the attraction between the two particles that would hold a solid in place like this is not there with a liquid, and so these particles can move freely around each other, and so this would be able to be poured. Whereas if you have a gas, then the particles are very spaced very far apart. They're allowed to move freely about each other. But what's actually the difference, and what causes this difference? And so we would have solid here. Well, as you start to increase the temperature of a material, and we have a lower limit of temperature, and the coldest that you can ever go is minus 273 degrees centigrade, and that's it. That's the lower floor. You can heat things up as much as you want, but the coldest temperature that you can get that is possible is minus 273 degrees centigrade, and that seems like a bizarre number. Why that? Well, this is defined as, because this is the temperature, but it's defined as all particles whether in a solid, liquid, and gas, will vibrate. And so this particle, it's sitting here, and it's going to be vibrating back and forward. It's just going to be vibrating. The colder temperature that you get, the less heat energy it has. And the heat energy, what the heat energy is a measure of the kinetic energy of the vibration of the particles. So the particles are sort of vibrating back and forward, and they're having kinetic energy. The colder you go, the less energy that it has. And so when you get down to 0, we would say that the kinetic energy of the particle is 0, i.e. it's not vibrating anymore. And now that explains why there's a limit to how cold we can get, because you can't get slower than not moving. You can't get a slower or a less kinetic energy, because you could slow it down, it could stop. It can't sort of go into a negative motion, because then it's just moving. So the lower floor of what we have is minus 273 degrees, and we'll talk about this a lot more a bit later on in the course. But for now, when they stop vibrating, that's the coldest it can be. And so solids here, they vibrate the least, but they still vibrate. And so you'll have all these solid particles, and they're all jostling around, vibrating. And the vibrations are microscopic. You look at a pen and you don't see it vibrating. And so that's a ridiculous thing. So the actual particles, they're tiny, and the vibrations that they're doing are tiny as well. But nevertheless, vibrating they are. Now, as you provide more heat energy into a solid, the particles start to vibrate more and more and more and more. And eventually they start to vibrate so much that they start to sort of shake loose, which would then put them into a liquid. So a liquid, they're just vibrating a little bit more than what the solid was. They have more energy within them. Okay, so as temperature increases, the heat energy also increases. But definitely when we're talking about heat, we're talking about the energy contained of the particles. And heat energy, we're looking at the vibrations of the particles involved. And as you heat more and more and more, excuse me, as you heat more and more and more, eventually the vibrations become so much that then the particles start to break free, and they'll be flying around all in random directions, and they can be moving around in a free state. So we have heat, we have temperature. And as I said, this is the coldest that you can get. And what we have is that we have our degrees centigrade scale, which is our SI unit, but we also have a different scale. We have something called Kelvin. And Kelvin is just an adaptation of this scale, really. But because this is the coldest you can get, and you'll find out why we do this a bit later on as well. But because Kelvin is the coldest you can get, we just say that 0 Kelvin, so 0K, which is the unit for Kelvin, 0 Kelvin is equal to minus 273 degrees centigrade. And so 1 Kelvin would be equal to minus 272 degrees C. 2 Kelvin is equal to minus 271 degrees C. And I'm not going to go all the way up to 0 degrees C, but I will say that plus 273 Kelvin is equal to 0 degrees C. And so we have our course notes, and in the first page of the course notes, there's some practice conversions for you to do. And all you're going to be doing is to convert from Celsius to Kelvin, you would add on 273. And so, well, if I go to this, you're going to just be doing 22 plus 273, which would give you 295. And we're going to Kelvin, and so we would just write big K. And similarly, to convert the following from Kelvin to Celsius, you would take away 273. And so you would have 67 minus 273, and that would give us sorry, sorry, there's a bit of a brain malfunction there. So we would have minus 6 degrees C. Okay, I hope, yeah, that would be correct. Yeah, okay, so I'll rewind that bit and do it again. Maybe I won't. Okay, yeah, so minus 6 degrees C. So just take away take away 273 from whatever value you have there, and you'll get that converted back from Kelvin into degrees centigrade. Okay, cool. So heat and temperature, that's the difference between the two of them. You can go through, do the questions, and have a load of fun doing it, I'm sure. All right, thanks for watching, and I'll see you again soon. Bye.